for the next many classes, we will always be kind of all we are doing is to basically move around first law of thermodynamics and develop more and more intuition for it. So it says that d of u, which is a state function, is equal to the heat given to the system and work plus work done on the system. And remember that this is a state function which does not care and this on whether the heat was given to the system or whether work was done on the system. And the state function itself comes from the potential plus kinetic energy. So for ideal gases of point particles or of molecules, it's easy to write it down. For non-ideal gases, it becomes a bit complicated. This Q and W are in a certain way for the system, Q and W are similar. The system cannot tell whether it got energy by heat being given to it or by work being done on it. But remember, we saw a difference early on that Q corresponds to energy that comes from random movement in the surrounding, right? Gas molecules are just randomly bombarding around, while work comes from organized movement. This is the difference. And this random aspect of heat is something we will visit a little bit today. And once we start doing entropy, it will really play a big role on that. This heat is random. It's something hard to control. So we saw a problem last time where we talked. So last time we talked about the isothermal expansion of an ideal gas. Are any of you coming to the chemistry barbecue today? Good. Don't ask me 481 questions there. You can. So we were thinking about pressure volume. For those who don't know, it's happening 3 o'clock in this atrium area. If just go around, you'll smell barbecue. Just come for it. I don't think it's good if you have RSVP. If you have not, it's still okay to go. And there is going to be a steel drum band or something. So you have a gas which is expanding from volume VI to volume VF. And we talked about a final pressure PF and an initial pressure PI. And we talked about how if it expands reversibly, it follows this curve. And if you just expand it, like directly apply high pressure, then it goes around this curve. And then we saw that the work, and since it is expansion process, we know the system will be doing positive work on the surrounding, right? So expansion means system does positive work on surrounding. And we saw that if we are interested in the work that happens during the reversible process, let's actually, in the reversible process, that is the red shaded part. And if we do the whole thing, directly take it to the very, very high pressure, then it becomes an irreversible process, right? Because change happened very quickly. Change was not quasi-static. So the other word that is used almost synonymously, there might be some differences, but for this class, it's basically same, reversible or quasi-static. So W reversible, when we compare it to W irreversible, and this we are talking about in this case, I'm asking you about work done by the system. So I'm talking about two positive numbers. Okay, so think carefully. Which one was larger? Reversible work or irreversible work? Huh? Reversible work, right? Which was the area under the curve. If I had asked you about work done on the system, then which one would be larger? Irreversible. Then we are looking at the negative of that thing. So it becomes confusing. This positive and negative convention, it is confusing. There is no period. You have to be very careful in how you write it down. So if we are talking about work done by the system, the W reversible is more. then W irreversible. So the red shaded area is more than the green shaded area. However, in both processes, the system went from PI-VI to PF-VF. Did the internal energy in the reversible process and the internal energy, let me again write it down in colors. Actually, I don't want to use colors for a reason. That is your hint. So the internal energy change in the reversible process and the internal energy change in the irreversible process as the gas goes from this I point to F point, which one is larger? Who thinks left is larger? Who thinks right is larger? Who thinks both are same? Oh, you guys are all pros, that's awesome. Why is it same? U is a state function, right? It just doesn't care what path you take. This is always going to be same. So the question is, where did the difference go? How do we reconcile it with the first law of thermodynamics? What is different then? Heat. So in one of them, the system lost more heat to the surrounding. Which one? In the irreversible one. When you do irreversible change, the system loses more heat. This is quite an intuitive concept, right? When you are running a battery or a machine and you want to get some energy out of it, if you don't run it efficiently, a lot of heat goes away. And heat is bad. Heat is dissipated. And you can almost see the reason why heat is bad, in fact, that running an air conditioner is typically way more expensive than running a heater. It's way easier to heat rooms than running an air conditioner. Heat is something which is, we can't control it. It's a random movement. So in this, and again, we have to be careful with the sign. So I will write it down in words. More heat is lost from the system during irreversible change. So it's not that the reversible change, there is no heat loss to the surrounding. There is heat loss to the surrounding, but it's more heat is lost to the surrounding during irreversible change. So if you really want to get comfortable with 481, I recommend that at home, work through these relations. Think about all the positive signs and the negative signs. Here, I'm kind of doing back and forth, right? I'm talking about heat lost from the system, while in my first law of thermodynamics, I defined Q as the heat given to the system, right? So look at all the expressions, work through it, and make sure you really understand it all. If you can do this, a lot of the problems that you're going to face ahead in 481 will be trivial. Otherwise, they will seem a bit complicated. Any questions? So this almost makes it sound like heat is bad. We don't care about heat, right? It's dissipated. We want to run an engine. What we want to do is to get more work out of it, right? If I could, I like to go for runs. If I could run by eating only 200 calories a day, that would be super efficient, right? I could, if I ate 2000 calories, I could just keep running and running and running and running. But that doesn't happen. I'm inefficient. And this inefficiency is basically heat. And one reason, for example, does anyone know why humans are much better long distance runners than almost any other animal? Where are the biochemists? Are you a biochemist?
Yeah, don't sweat.
Right. Yeah, we are way better at sweating, right? So all this Q that is being lost, we have a way of dissipating it. While other animals, dogs, for example, my dog, he likes to sprint as fast as he can and then just stops. Can't do anything. It's like, oh no. It's like first law of thermodynamics is catching up. I cannot do anything. I should have attended 481. So you're absolutely correct. You know, that's because we can sweat. We have a way of getting rid of this heat. So in this sense, if you're trying to think about how efficiently you can run a system, heat is bad news. But heat is not always bad news. When you're trying to investigate a system, then heat is typically the probe through which you investigate it. Let's say you made some very complicated protein, I don't know, something that looks like this, right? And you made this protein and you want, this is a protein. or some mixture of protein and a DNA or whatever it is, okay? Some molecule. And you made it in the lab and you cannot see what exactly it is. You want to study what are the nature of interactions inside this molecule, right? In order to do that, what you would like to do is to come up with the internal energy of the molecule. Why do you want to come up with the internal energy? Because if you can study the internal energy, then you can go back and calculate how does the potential energy of this molecule change as a function of distance. You can see whether there are long range forces, there are short range forces, right? So often, so the point I'm making here is that Q is bad news when we want to run an engine. An engine is a very generic word used in thermodynamics. A cell is an engine, a muscle is an engine, a car is an engine. In that case, we want to minimize heat loss. Q is useful when we want to study a system. So we have this arbitrary system and we want to study what is the nature of internal energy inside it. So we know that if we can calculate delta U, if we can construct a process where we can directly measure how much heat did we give to the system, and it doesn't matter what path we take in order to give this heat, at the same time we see how much work had to be done on the system, then that always sums up to the internal energy of the system, right? Any path. So in this case, heat is useful when you want to study a system. So that's why we introduced the notion of heat capacity. So then we said last time that we defined heat capacity last time. I'm not going to write down the definition again. You can see last time we defined it. And we specifically defined two types of heat capacity. One was heat capacity at constant volume, which was the change in heat that you need to provide to a system, the amount of heat you need to provide to a system for a unit change of the temperature when this process is carried out at constant volume. Okay. Now, similarly, we can write down Cp, heat capacity at constant pressure, is equal to partial Q by partial T at constant pressure. Now, here is a subtle but very important question. We are saying that Cv is the heat given to a system at constant volume. Is there only one type of, so when we do something constant volume, we are specifying something about the path that the system should take, right? But is there only one path that is constant volume, or can you think of many, many paths being constant volume? There is no reason to think that there is only one path that is constant volume, right? Something else might be going in the system. So from this definition, it is not obvious why all constant volume paths should have the same Cv, right? Because up in the numerator here, we have a path function. So we are differentiating a path function with respect to temperature, and we are saying, doesn't matter which constant volume process you take, they should be the same. How do we prove that? In order to do that, we look again at du is equal to y is Cv path independent. So we look at du is equal to delta Q, and we focus only on pressure volume work, okay? We will ignore the other work. If it's a constant volume process, what can we say about dV? 0. So delta Q is equal to du because dV is equal to 0. And my V is looking dangerously similar to. Therefore, Cv, constant volume, is equal to partial derivative of a state function with respect to temperature at constant volume. And now we have a state function. Hence, when you differentiate a state function with respect to something else, it is still going to stay a state function, okay? Is equal to state function. So it does not, if you're talking about Cv, it does not matter about which particular path did you take in order to keep it constant volume. Later, we will be seeing examples of different paths which are constant volume. So let's talk, so this equation is very important. Let's call it equation number 1, okay? This is something we will be looking at again and again and again, that CV is equal to partial U by partial T at constant volume. So example of CV. Ideal gas is equal to number of degrees of freedom multiplied by RT by 2, right? So for an ideal gas, U is equal to number of degrees of freedom multiplied by RT by 2. Therefore, CV is equal to partial U by partial T at constant volume is equal to number of degrees of freedom R by 2 is equal to independent of temperature. And as I mentioned last time, this is not true for most materials. The CV tends to follow a very complicated behavior at low temperature. And that was a triumph of statistical mechanics and quantum mechanics in early 20th century. It took Einstein and Debye and all these people. Actually, Einstein got it kind of wrong. It was Paul Debye who got it perfectly right, that how CV depends on temperature. But we are not going to talk about that right now. We just know that for an ideal gas, we can write down what is the CV. And you can get lots of fun problems where you have to calculate NDOF for different molecules and you will get different CVs. Later, we will talk about CP also and the connection between CP and CV. But for now, this is what we have for an ideal gas. So here is a question just to test your understanding, whether you are, how comfortable most of you are feeling with partial derivatives. Does this equation number 1 imply du is equal to CV dt? Who thinks this is wrong? Who thinks this is right? No one thinks this is wrong? I have removed partial derivatives with total derivative. It's wrong. Let's see why it's wrong. It's confusing, okay? So if you thought that it's correct, don't be sad. It does look correct. And in exams, this is like a #1 mistake students make. They just write it and they think, oh, there is no need to do all that math. I got the answer right here. Why is it wrong? Let's think through it carefully. Why is this wrong? Except ideal gas. For ideal gas, we will see this is true, but for everything else, this is wrong. So let's think about U as a function. What do we need? What can we write U as a function of? We can write U as a function of V, T, N, and pressure, right? For constant composition, which I said we are going to be really worrying about only constant composition systems for a long time. N is equal to constant, so we can ignore it. So it becomes U is equal to V, T, and P. On top of that, we know that under equilibrium, we don't need all three. Don't need all three in equilibrium. So we could write it down as U as a function of volume or temperature, U as a function of temperature or pressure, U as a function of volume and pressure. Now, does anyone see why that equation is wrong? Go ahead. Exactly, you will need the second derivative. So let's consider this one. This one tells us that du is equal to partial U by partial V at constant temperature multiplied by dV plus partial U by partial V. No, I wrote the same thing again. Partial U by partial T at constant volume multiplied by temperature, right? When you have a function, if U and V and T are confusing you, all I'm saying is if f is a function of x and y, then the total derivative of f is given by partial f by partial x at constant y multiplied by dx plus partial f by partial y at constant x multiplied by dy. This is the definition of a total derivative, right? And if you look at that, what does this mean? This means that du is equal to this thing is CV, right? What we wrote above. So this is CV dt plus partial u by partial v at constant t multiplied by dv. So this equation over here was missing this second term. So why is, but I also said that equation is true for an ideal gas. Anyone see why is it true for an ideal gas? Why does the second term become 0 for an ideal gas? Someone who has not answered. Go ahead. U has no dependence on V, right? For an ideal gas, we just wrote over here that U is just a function of temperature. So for an ideal gas, U, partial U by partial volume at temperature is equal to 0. Therefore, du is equal to Cv dt. In general, du is not equal to Cv dt. This is always true. Always true. This is how partial derivatives start to become confusing. So you are in prime partial derivative confusion land, okay? So stay with me or it will get more and more confusing. Let me write it down once again. Cv is equal to partial u by partial t at constant v, always true. Ideal, non-ideal, whatever. However, du is equal to Cv dt only for ideal gas. And in general, du is equal to Cv dt plus something multiplied by dv, and that's going to be partial u by partial v at constant t in general. So let's, how far did we go? We had equation number 1. Let's call this equation number 2. So this equation number 2 is true in general for anything, any material. You have a DNA, you have a protein, you have a complicated cell, anything in the world you can imagine will follow this equation. It's super powerful. It's always true. And it's so powerful that this term over here is given a name. Partial U by partial volume at constant temperature. What should we call it? What is the change in energy with respect to volume? Can you think of a physics quantity that corresponds to how energy changes with respect to volume? If you did a dimensionality analysis, what would you get? You will have to write it down to just work through the units. Go ahead. Pressure. It's a pressure. It's not the P, the external pressure. It's an internal pressure. It has the dimensions of a pressure. It's not quite the pressure. It's got the dimensions of a pressure. And you can calculate this for a van der Waals gas, and you will see this is the attractive force being experienced by the molecules. And we will get to that in a moment. So this thing is called the internal pressure. Okay, let's mark it. This is an important equation, equation 3, and it is given a symbol pi t. That is the symbol for internal pressure. Pi as in this circumference by diameter of a circle, the ratio that we all love. Pi with subscript t is the internal pressure. So we just said, so this equation 2 can be written as 2 is same as saying du is equal to Cv dt plus internal pressure pi t multiplied by dv. This is also true in general. And here is a problem that you can easily get asked on an exam. And if you don't have notes or anything, you could get confused. Internal pressure for an ideal gas is 0. Why? Because once again, U is equal to NDOF RT by 2 for ideal gas. Therefore, partial U by partial volume at constant temperature is equal to 0. Is there anyone who plays classical music in the audience? Some people. You know, I always sucked at playing music. I tried to take classical guitar for like 4 semesters, and I sucked. Because anytime I would go, I would just see sheet music and I was like, this is not music. What is this garbage? Thermodynamics tends to look a lot like that. If you look at the notes, it just looks like, where is the physics? Where is the chemistry? It's just a bunch of equations, right? But every equations carry some meaning in it, right? And you have to stick with it. So that's why I keep bringing this sheet music analogy. Don't be like me. Don't give up on music. Don't give up on thermodynamics. Stay with the sheet music. Think through the problems and you will get intuition. But this is the language. We are all basically learning the language right now. So this equation that I wrote, we can draw it. Typically, graphs tend to be a bit more intuitive, just like we saw for the work done thing, right? It was very intuitive to look at this graph and see why you can get more work out of a reversible process than irreversible. So let's do this over here. Let's plot the internal energy of an ideal gas versus volume. Internal energy of any gas versus volume. How will it look like for an ideal gas? Anyone who has not answered? Huh? Go ahead. Are you sure? Vertical or horizontal? Horizontal. Yeah. It's independent of temperature, right? Independent of volume. It just depends on temperature. So if you calculate the slope of this thing, and we are talking about internal energy at constant temperature. Of course, if the temperature is also changing as you are changing the volume, then it won't be constant, right? So for a constant temperature process, it's going to be constant. If, however, you make a fancy material where you find that your internal energy, let me use green, looks like this. At constant temperature, your internal energy increases with volume. Now think through it carefully. In an ideal gas, there are no attractive forces, right? We all know that you don't talk to each other unless you are sitting on top of each other. Otherwise, you don't care. I just made a material, and let me draw it once again very clearly here, where you measure the internal energy as a function of the volume of the system. And you find that as you compress the system, the internal energy goes lower and lower and lower. What does it tell you about the nature of forces in that system? Are they attractive or are they repulsive? Huh? Why?
There's less energy as they're compressed.
Exactly. Exactly. It's like if I did the classroom, made it smaller and smaller and smaller, you are getting happier and happier and happier. Yay, yay. That's not going to happen, right? So if it was indeed true, if I don't know, if you were a bunch of dogs or something, they seem to be very happy. They like to really go and sit in one corner. You guys, on the other hand, would behave something like this. If I made the classroom smaller and smaller and smaller, you would get very unhappy, right? Repulsive forces would start to dominate. So by measuring how the internal energy changes as a function of volume at a constant temperature, you can see whether the system is primarily, let me use a different color. If the system is primarily made of attractive forces or repulsive forces, and it doesn't have to be the same curve all through, right? Maybe at certain volume, maybe let's take your example. If you are in a football field and I start to compress the football field, you might get happier, right? Because you cannot talk to each other. But at some point, it could get more complicated. So for you, it might, for you all, the curve might look something like at very large volume, it's attractive, and then you go, whoa. This is quite the curve for a real molecule. This is what we drew. Remember, this is how we said. That's the whole idea there. That when you're very far, long-range forces dominate. You want to come close. It could be volume or it could be R, the distance. But once you get very close, your electrons start to repel each other. And you say, no way, get away. So now what can we say about pi t for these two plots? What will be pi t for this one, positive or negative? pi t is how the internal energy changes with increase in volume, right? So pi t is positive. And in this case, pi t is negative. So that's kind of fun. The most interesting thing is, and I think you will be doing it in this homework, I don't know if I gave it, or you will do it later. If you write down Van der Waals equation of state, see, I always forget how to write it. Ideal gas is PV is equal to nRT, right? So Van der Waals equation of state is P is equal to nRT by V minus NV. And then we have a negative term because attractive forces decrease the pressure multiplied by density squared. You can show that for a Van der Waals gas, this is pi t. I don't think this is in this homework. Last year, actually, I gave this problem in the homework. And then at least 3 students in the class who were really enjoying the class pointed out to me that you cannot prove it using only internal energy. In order to prove that the internal pressure for an Van der Waals gas is equal to minus AN square by V square, you have to have the concept of entropy. If you don't know what is entropy, you cannot prove this. And this is really remarkable that you cannot prove this. In fact, I can mathematically prove that you cannot prove this. It sounds strange, but it is due to loss of information. So, and I will make this note for later. Later, we will see that pi t is equal to minus AN square by V square for Van der Waals gas. This cannot be proved without entropy, without the concept of entropy. And I will give you a flavor for why that is true. Remember how I mentioned that U can be written as a function of Vt, Tp, and Vp, right? Later, we will find that U can also be written as a function of entropy, pressure, and volume. And it turns out that one of these definitions carries more information than the other definitions. That definition is known as an information theoretically complete definition. We will get to that later, not for now. For now, just this is going to be a homework problem in the future. Try doing it without using the concept of entropy. Specifically, try the reason how the students discovered it because they tried to Google for a solution, as we all are guilty of, and that's okay. And they found that all these solutions on the internet use something called the Maxwell relation, which you saw in the first homework, which involves entropy. And they're like, oh, okay, but we haven't done entropy. So on Slack, I started getting bombarded with messages. Can I solve this problem using Maxwell relation? And turns out you cannot show this without using Maxwell relation. You have to have entropy. That's amazing. For now, let's come back. So what have we said so far? We have said that du is equal to Cv dt plus pi t dv, and this is equal to 0 for ideal gas. So what we talked about so far is heat given to a system at constant volume. And that can be done in a furnace, which is of constant volume. You need to have a heavy duty furnace in which something is going down and things are happening. And then you can measure heat capacity at constant volume. Often, when you're thinking about the human body, how the reactions that are going inside us as we are talking to each other or listening, are these really constant volume processes? Does a cell operate at constant volume? Probably not, right? That would be terrible. I mean, the pressure could build up so high. So how does a cell really operate? That's a complicated thing. A cell is probably not even in equilibrium. Things are changing very much. But if you did have to approximate the cell as an equilibrium process, a constant pressure process might be more respectable for doing that, right? The volume of the cell is changing in order to keep a constant pressure. In fact, that's why our blood pressure oscillates around a certain value, right? So, or a better example of constant pressure is doing a reaction in something like this when this is open, right? This is constant pressure if this reaction is going on. Why? What is the constant pressure? It's the atmospheric pressure. Excuse me. But if the reaction is going on in this, then it's a constant volume process, right? I have shut it tight. And at some point, if it's a really funky reaction, it could break this thing in different pieces. I mean, how many of us here have experienced the joy of putting a beer bottle or a beer can or a Coca-Cola can in the freezer, right? You know what happens. You're like, oh, I will cool it quickly. And then you forget and you come back 5 hours later. Does the same happen if you put an egg in the freezer? Does it explode? Egg. Would an egg explode in the freezer? Exactly. Exactly. Because as we know, one of the craziest things about water is that it expands when it freezes. So you can have the same experience by putting an egg in the freezer and it will blow up, right? So I got distracted. Let's come back. Let's talk about heat at constant pressure. So for that one, the symbol we use is again C for the heat capacity. So how much heat do you have to give to a system in order to increase its temperature by a certain amount at a constant pressure that is known as heat capacity at constant pressure? So the first question now is, we saw earlier that the heat given to a system at constant volume is the same as the change of a state function. What was this state function? Delta U, right? So when I was teaching this class purely on Zoom, I would give a pop quiz right around now. And it would be awesome. I can't do it right now. The question then is, at constant pressure, is there a state function, the change of which corresponds to Q? It's not obvious. Why should it be the case, right? Turns out there is a state function, the change in which is the heat given to the system at constant pressure. And this state function is the next state function that we are going to talk about now. It's got a name. It's called enthalpy. So when you are doing a chemical reaction or anything at constant pressure, it's better to think about the change in enthalpy of the system rather than change in the internal energy of the system. And we are now going to show that H, which is defined as internal energy plus pressure multiplied by volume. This is the definition of enthalpy, right? Why did we write this definition? Why did we not write U minus PV? U minus PV would also be a state function, right? Does anyone disagree with that? Does anyone disagree that U minus PV is a state function? Everyone agrees? It's a useless state function, okay? It doesn't help with anything. U plus PV, on the other hand, turns out to be very, very useful. And we are just going to show that with this, gives indeed delta Q is equal to delta of U plus PV at constant pressure. It's not going to be true all the time. At constant volume, it won't be true. And if the heat is being given in some funky manner, it won't be true. Only at constant pressure, this will be true. Before we derive this, let's try to think about something very, very intuitive, which is, which one will be larger, CP or CV? So let's imagine a system. And in this system, we have some gas. And in one case, imagine that heat is given to this gas. Heat given. In case one, this is fixed. So constant volume process, okay? In case two, not fixed. So in case 2, this can move up or down. In which case will you have to give more heat to the gas for the gas to change its temperature by 1 Kelvin? You have an idea? Exactly. You're absolutely correct. What's your name? Stella. Stella is absolutely correct. In case 2, when you give heat to the gas, it moves up against the surrounding. It's like I can do something, right? So some of the heat given to the gas will be lost in doing work against the surrounding, right? Which sometimes is something we want to do, and that's okay. But if you have a constant volume process, that is not true. So Cp is more than Cv always. Why? Under constant pressure, some heat given to the system is used up as work against the surrounding. In constant volume, we know pressure expansion work is 0 because dV is equal to 0. There is no work. So all the heat that you give to the system goes into changing the internal energy of the system. Okay? And that's why Cp is always more than Cv. Now, how much more? That's an interesting question. We will later be able to show that Cp minus Cv is equal to NR, where N is the number of moles of the system. It's related to number of degrees of freedom, and we will get to that later for ideal gas. But even for general gas, we can write down this exact equation as to what is the connection between Cp minus Cv. Once again, it involves the concept of entropy, which we haven't done yet. We will get to that in a moment. This we will do later. But for now, intuitively, it should be clear, just like Stella said, when you're giving heat to a system, and if this system can move up and down, if the against the surrounding, it will do some work, and some heat will be lost to that. So in fact, I have the relation here. Later, we will show that this is equal to thermal expansion coefficient squared multiplied by temperature multiplied by volume divided by the isothermal compressibility. And this is exact. This is true for any material in the world. And we will be able to prove this. These are constants, right? Thermal expansion coefficient you can measure. So don't worry about these coefficients. These will all come later. We will actually prove this later. So lots of fun to be had. So now we have to show that H is equal to U plus PV, the state function we defined, indeed gives us delta Q is equal to delta H at constant pressure. How do we do this? This is a bit of algebra. Let's work through it and then we will be done for today. So first thing, we have to agree that H is a state function, right? Because you have taken U, a state function, pressure and volume are state variables. So all is good, which means we can talk about, we are talking the proof here. We can actually talk about D of H. We don't have to talk about little squiggly of H. We don't have to do what we did for Q. We can talk about D of H. So D of H is going to be D of U plus PV is equal to DU plus PdV plus VdP. At constant pressure, we can remove this term, right? dP is equal to 0. So this is du plus PdV at constant P. dP is equal to 0. For first law of thermodynamics with pressure volume work, du, and let's number this equation, sorry. Let's call this equation 5. So first law says that du is equal to delta Q minus PdV, right? So use 6 and 5. What do we get? dH is equal to delta Q minus PdV plus PdV. Oh, It canceled at constant P. If it was not constant P, we would not have been able to get rid of this term, right? Therefore, dH is equal to delta Q at constant P. It's a simple algebraic proof of why the change in enthalpy is equal to the heat given to the system at constant pressure. Therefore, Cp is equal to, what is the definition of Cp? The definition of Cp is this thing, which can be written as partial of H by partial of temperature at constant P. And we also saw that heat capacity at constant volume, which is this thing, is equal to partial U by partial T at constant V. And as we go further, these two equations should become your second and third best friend. Which equation should be your first best friend? First law of thermodynamics, right? Don't forget that. If you forget that, then it's game over. So, and I will shut up after this. We can say that delta U is equal to delta Q at constant volume, and delta H is equal to delta Q at constant pressure.